Now that we've seen the increases in the greenhouse gases and due to the increase in population, what does this mean for the future? Well, if we want to look at what may happen by 2050, we need to use climate models, what we call GCMs, which could be translated either to global climate models or general circulation models. These models are basically simulations of the entire climate in the whole globe, both the atmosphere and the oceans, and we have to divide the planet into pixels like you have on your digital camera. And each pixel, we have to define how big that pixel will be, but it's normally, say, around 1 degree longitude by 1 degree latitude, which is approximately 100 by 100 kilometers. And in every box, we have to simulate all of the processes which are happening both in the atmosphere, the land surface, and in the oceans, like we can see in this diagram at the bottom left. So we have to simulate the currents in the ocean, we have to simulate the vegetation, the type of vegetation, how this interacts with the greenhouse gases, the land ice, the sea ice. We have to generate clouds in the model which will produce rainfall, and the winds which will transport things around the planet, the interaction of the sunlight with the greenhouse gases and dust and particles in the atmosphere. And this we have to do at every box and at every time step. So if we want to predict what will happen in 2050, we have to recalculate all of our equations every, say, 1 hour during the day, and then for every day, every year, going into the future. Now, you may say, how can we predict what will happen in 2050 if we can't predict the weather next week? Well, there's a big difference between the weather and the climate. The weather is very noisy and chaotic, and so it is difficult to predict the weather next week. But the climate is the average of all that weather. And so I can easily predict, say, that it will not rain in August 2025 or 2030 in Israel. I'm giving an average forecast for the future. I can say also the range of temperatures, perhaps. I can't say what's going to be on the 3rd of August in 2030, but I can say fairly confidently that we won't have rain in Israel in August 2030. So when we're looking at the future climate, we're looking at the average climate. We want to predict what's going to be the average temperature, the average rainfall, maybe also the variability of the rainfall, sea level rise, the humidity, many other parameters. And so these models can actually give us some information about what may happen in the future as a result of the increase of greenhouse gases in the atmosphere. But before we predict what will happen in the future, we have to check if these models are any good to predict the past. We know what happened in the past. We've seen this. We've shown you the data already. And here you can actually see the temperature changes, the global temperature changes shown by the black line in both of these plots over the 20th century. So from 1900 to 2000. And on the top, we see all the different models around the globe. There are maybe 50 groups which have these models, different models. The yellow individual line and the red line on the top is the average of all these models. At the bottom, we see also simulations from these models in blue with the average in dark blue. What's different between the two is the bottom curve shows the model with only the natural things happening in the model to influence the temperature. So ocean currents, volcanoes, and actually the volcanoes are shown here by these gray vertical lines. Because when we have big volcanoes in the atmosphere, not all volcanoes, the specific type and intensity of volcanoes, and they put up very small particles in the upper atmosphere, they actually cool the planet for a number of years. So we can see after each of these vertical lines, the temperatures actually dropped for a number of years. And again, we're looking at the temperature anomaly, the changes over time, not the absolute temperature. And again, we can see that from 1900 until 2000, approximately a 1 degree global warming shown by the black curves. And the model, in the top model, we see basically everything. So the bottom plot again in blue is only the natural causes of temperature change on the planet. And the top plot shows those natural ones, and in addition we add the greenhouse gas increases because of man-made activity. And what we see is that the top plot, the red curve, matches fairly nicely the black curve, whereas in the bottom plot, we see that from the 1950s and 60s, the bold blue curve actually diverges and is starting to decrease. And in fact, if it wasn't for our man-made activities here, we would have seen a cooling of the planet at the end of the 20th century. And so these models are actually very useful because we can switch on and switch off all processes, different processes in the model, and we can actually see what would the climate have been if we didn't interfere with the climate, and we wouldn't have put all these greenhouse gases in the atmosphere. And that's what we see at the bottom. And if we do include all the man-made influences, then we can see that we get this global warming, which matches very nicely the temperatures. So in this way, we can have much more faith and confidence in the models that if they can duplicate what we've seen in the last 100 years, the last 200 years, and even longer, then we can maybe use them to give us some information of what may happen in the future. So here we can see some now simulations into the future, what may happen with global warming by the end of the century, 2100, and this is published in the IPCC report in 2021. And what we see here, that there are a few options, and those options depend on what we do. So we have some optimistic scenarios, the very low emissions, the bottom blue curve, which says that we rapidly move away from fossil fuels and move to renewable energies, clean energies, and therefore we may reach a maximum warming around about 1.5 degrees, around about 2030, 40, and then things will start to cool off again. The uppermost plot in the very high emissions are basically continuing as business as usual, using fossil fuels and basically not changing our ways and going into the future. And that prediction says that we could warm up by about 4.5 degrees by the end of the century. I'll just remind you that in the last ice age, 20,000 years ago, the global temperatures were about 4.5 degrees cooler than today, and that resulted in a 100-meter drop in sea level, ice sheets all over Canada. And so a 4.5 degree warming in the opposite direction will have a dramatic effect on the climate, but instead of happening over 10, 20,000 years, it's happening over 100 years. So very dramatic. But that's also fairly unlikely because we already see significant changes in the use of renewable energies, moving to electric cars, and so it's likely it'll be somewhere here in the middle. The scenario won't be the most optimistic, won't be the most pessimistic. So around about 2 to 3 degree warming, global warming, by the end of the century. Now, if we look at what's expected to happen in our part of the world, in the Mediterranean region, shown in green here on the plot, again, we can run the model back in time, and we can see the observations by the black curve until the year 2000. The red areas, the variability from the different models. And then in yellow, we can see in orange the prediction going out to the end of the century, and the different models shown, the range of the models on the right-hand side. And we see that it's likely that the Mediterranean will warm by about 4 degrees relative to 2000 over the 100-year period, a dramatic warming, and we call the Mediterranean and our region a hotspot because it's actually going to warm more than the global mean, with all the implications that will come with that. And here we can see an animation which goes from the 1800s to the present, but then will continue for the model going out to 2100. Again, the clock and the dial of this clock are the months of the year, going from January to December. And you can see the circles which represent the global warming for every month as we go into the future. And we can see that this is with one of the scenarios of the IPCC, that if we keep burning fossil fuels and going on as business as usual, we could reach about 4 or 5 degree warming globally by the end of the century. And again, if this happens, we'll have a dramatic different climate on planet Earth with very negative implications for all of us here. Now, when you talk about global warming of 1 or 2 degrees, 3 degrees, still people say, well, that's not a lot. We go from day to night, summer to winter, maybe 10 degrees, even 20 degrees changes. Why should we be worried about a 1 or 2 degree warming? So here we can see, for example, that the distribution of temperature, say in Tel Aviv, showing that we have an average value. We have average temperatures. We also have cold days, and we have warm days. And if we shift this just by a few degrees, what happens, we don't always notice the average, the mean temperature, but all of a sudden we get a lot more hot days. And we also get, at the tail of the distribution, we get some very hot days that we haven't experienced before. heat waves, which can result in droughts and other phenomena. And so the shift of just a few degrees, we actually feel that in the extremes, that we have much more extreme temperatures or maybe extreme rainfall patterns. And this is what's worrying, because it's the extreme weather and the extreme conditions which are what we can actually feel and which are actually most harmful to us. And we see it's happening. So here we can actually see data of the distribution of temperatures for every month of the year from January to December. And the blue and the orange distributions here for global temperatures are separated by 100 years. Each of the distributions is 30 years. So in the blue, we're seeing temperatures for every month from 1881 to 1910. And the orange is the temperatures from 1981 to 2010. And we can see that the temperatures have shifted to warmer temperatures. And again, this is about the 1 degree global warming that we see. And if we just look at some of the more recent data from 2016, 2017, the little boxes on the right, those are the global mean temperatures in those years. And all of them are far out to the right-hand side, even warmer than we saw from the 1980s to 2010. And nearly every year we're breaking records and we're putting on more points on the right-hand side of these distributions. So we're seeing this happen, a small shift in the mean, but this keeps going towards the right. And if we look at one example of how this can impact us, in 2003, the summer of 2003, in fact, only about 10 days in that period, we had an extreme heat wave in Europe. On the right, you can actually see the temperature distribution shown in green for Switzerland. From 1863 to 2003, the average temperatures in the summer, and each of those vertical lines is actually an individual year. But in 2003, this distribution shifted about 5.5 degrees to the right, that red line. It still was only 22, 23 degrees, the average temperature, where for people in the Middle East and in Israel, this is very nice, cool summer. But in places like Europe, and we can see the largest warming was over France, but also in the UK, Italy, and Spain. In 2003, even hotels in Paris didn't have air conditioning, and we're not ready for such an intense heat wave. And the statistics show that more than 70,000 people died due to this heat wave in only a 10-day period. If we look at the mortality rate the year before and the year afterwards, 72,000 extra deaths occurred across Europe in this 10-day period in August and related to this heat wave. So you can see a small shift in temperature can have a huge impact on the people, on the health system, with death rates which can go up very dramatically. And this is one single event. We can expect many more of these in the future. The next thing the models predict is changes in rainfall. So we spoke about temperature changes, and basically all the models show we have a global warming. How much warming depends on what we do. And here we can see what the models predict for the end of the century for rainfall. On the left, we have the rainfall patterns, the changes in rainfall patterns for the winter, December, January, February. And on the right, we have the changes for the summer in the Northern Hemisphere, June, July, August. And here we can see there are two different patterns. There are areas which are going to get much drier than they are today, the oranges and the browns with up to a 20% decrease in rainfall. And we have the areas in blue and green which are going to get more rainfall in the future and become wetter. And in fact, the areas which are going to get drier are areas which are dry today, the subtropical regions, the Mediterranean, and the regions which are going to get wetter are regions which have enough water today. And we're going to actually have an amplification of the hydrological cycle, so that dry areas are going to get drier and wet areas are actually going to get wetter. What we can also see on this plot are these little black dots, if you look carefully, and this is where 90% of the models which are predicting this agree with each other. And so we actually have a lot more confidence in the areas with these little black dots, including the Middle East and the Mediterranean, where all of the models basically say we're going to see significant decreases in rainfall in the region, and we're already seeing it. If we look also at around the world, we're seeing, in California, dramatic droughts going on for many years, and problems with water resources there. But in other places, like in China, we're also seeing recently extreme flooding and heavy rainfall. And so we're getting both sides of the spectrum, much too dry in some parts of the world, much too wet in other parts of the world. And associated with that, we are seeing, and we also expect, a significant increase in extreme or severe weather. This is an area of my personal research. I'm looking at how thunderstorms and lightning may change over time as a result of climate change. But we see significant evidence already that the extreme weather events have been changing over the last decades, or increasing in number, increasing intensity, including tropical storms, tornadoes, hailstorms, flooding, and the damage, the actual economic damage, is also increasing dramatically with time. The last thing the models predict is sea level rise. We spoke already about the melting of the ice sheets, especially over Greenland and Antarctica. And here we can see the predictions for 3 different scenarios called RCPs, but these names change from IPCC report from one to the next. But we can see again the business as usual, which is this RCP 8.5, the high emissions scenario, and the low one at the bottom. And based on these, we can also estimate what may happen to sea level rise because of both the melting of the ice sheets, but also the warming of the oceans, and warm water takes up a larger volume, expands, so that also contributes to rising sea levels. And if we look at around about 2100, the end of the century, the estimate is that we could have a 1 meter rise in sea level, but it's not going to stop there. If we extend out to 2300, so in another 200 years, if we don't do anything, the sea level is just going to keep on going up, and it's possible we could get to 3-4 meter sea level rise. That may also not sound that much to you, but first of all, before we see the implications, let's see how good these models are. And this is the prediction the models gave in 1990, the first IPCC report. The gray area is the different scenarios, the range of scenarios for sea level rise, just 10 years later, in 2010. Now we have the data from then, and we can check how good the models are. And what we see is the satellite data showing rising sea level is at the upper boundary of the predictions of the models. And so the models actually may be underestimating what may happen in the future. Many people say the scientists are exaggerating, it's not going to be so bad. But the same as the models can overestimate, they can also underestimate. And here we have proof that maybe sea level rise is actually going to be worse than the models predict. What's the implication of sea level rise of just 1 or 2 meters? So here we can see close by to Israel, the Nile Delta in Egypt, the coastline of today in the top. And if we have a rise of 0.5 meter in the middle and 1.5 meters below, today there are more than 8 million people living within 1.5 meters of sea level in Egypt, in Alexandria, Port Said. And these people are going to have to be removed in their businesses, their homes. They have to be resettled somewhere else. That's today. The population will double probably by 2050. So we'll have 16 million people if the sea level goes up by that amount at that time. And this could result in another problem, especially in this part of the world, and that's climate refugees. These people won't have homes to live in, they won't have jobs. They're going to be looking for better places to live. And this could really result in a huge problem of climate refugees because of sea level rise. Another example is Bangladesh. So here we can see the coastline today on the left and what the coastline will look like if we have a 1.5 meter rise in sea level. 18 million people live within 1.5 meter. Again, these people are going to be displaced. They have to move, become internal refugees and international refugees, climate refugees. And in both of these regions, both in Bangladesh and in the Nile Delta, these are areas where there's a huge amount of agriculture, very rich land, rich soils in those regions, and this is going to be underwater. So not only are the people going to have to move, but this is also going to have dramatic impacts on food security or food insecurity in the future. So the models predict all the models predict these 3 basic parameters: warming, changes in temperature, changes in precipitation. Some places will get less, some places will get more, and rising sea level. And these we can then use these 3 parameters to study the impacts in many different areas of our lives, from health if we're looking at the distribution, say, of malaria or vector-borne diseases, even maybe pandemics. Look at agriculture when we're talking about the yields of crops, droughts, or pests like locusts, which can eat the vegetation and the agriculture and are influenced by climate changes. Forests, the health of forests, forest fires, for example, which are becoming more common. Water resources, the amount of water we have, the quality of water, the timing of the rainfall during the season, if we rely on the rainfall for agriculture in developing countries, maybe even conflicts over water in the future. Coastal areas where rising sea level is going to cause more erosion of the coastlines and more damage, and many of the megacities around the world are on coastlines. And also natural ecosystems, biodiversity, plants and animals, which are obviously impacted both by changes in temperature, sea level, and rainfall. I'd like to point out that when we've spoken that the greenhouse gases haven't really changed much over 10,000 years until today, till the last 100, 200 years. And all of our civilizations that we know of, if we're going back to the Egyptians, the Romans, the Greeks, all the civilizations we know have developed in this last 10,000 years, what we call the Holocene, a geological period of the Holocene. And again, if we go back 20,000 years, we were in the last ice age where sea level went down 100 meters. We came out of that, and that's when we started really developing our civilizations, the start of agriculture for our towns, our cities, not just for the individual. And this development of our civilizations occurred over 10,000 years where the climate was constant. Temperatures didn't vary that much. You can see the blue range of temperatures in the last 10,000. So there were slight ups and downs, but basically fairly constant, which meant the sea level was constant, which the rainfall patterns were more or less constant. And now we're leaving that Holocene. At the end here, we can see that we're coming out of this period that was being more or less stable for 10,000 years, and rapidly we are going up with global temperatures, which is changing rainfall, changing sea level. And again, based on the scenarios, we could be up to 4.5 degrees in just 100 years, not 10,000 years. So we're really going to see a dramatic change in the climate, which will have an influence on all our cities and our civilizations.